Let's dive right into problem 2 on the 2025 CompBC FRQ. First thing we'll note, of course, is that this is a calculator question. So we're given a curve C, which is defined by the polar equation r of theta is equal to 2 sine squared theta, and that intersects with the semicircle r is equal to 1/2. Now, part A asks us to find the rate of change of r with respect to theta at the point on the curve C where theta equals 1.3. And so let's get started on that. And we're going to use two separate approaches. Our first approach will be to do this without a calculator at all. Note that r of theta is equal to 2 sine squared theta. And we are looking for the r by d theta. And in this case, this is a straightforward application of chain rule. Outer derivative will give us 4 sine theta. Inner derivative will give us cosine theta. And so if we are looking to evaluate this at theta equals 1.3, then we can simply go ahead and plug that in. We have 4 sine 1.3, cosine 1.3. And remember that on AP Calculus BC, you're not expected to simplify your answers. And so there we have it. We're done. But note that in other similar problems, your derivative might not be as straightforward to compute. And so this is where we might want to do part A in Desmos. So let's hop over there. So I've gone ahead and plotted our curve. R of theta is equal to 2 sine squared theta. And it's actually very important for you to enter this as r of theta and not as r equals 2 sine squared theta. Notice that does plot the equation correctly, but my goal is to evaluate r prime at theta equals 1.3. So if we enter r equals 2 sine squared theta, doing r prime doesn't work. But if I now go ahead and write this as r of theta equals 2 sine squared theta, I can directly go ahead and compute r prime of 1.3, and that spits out an answer. So we've just done an entire part of our FRQ, part A, in about 20 seconds or however long it takes you to type this. Moving on then to part B, we're asked to find the area of the region that lies inside the curve C, but outside r equals 1/2. And so just to quickly sketch that out, that would be the area of this region right here. And so our first step is to determine the type of integral we're dealing with. As you may recall, there are two main classes of integrals in polar coordinates, one in which we break up into two separate integrals, each of which is bounded by one polar curve, and one in which we are subtracting our two polar curves. So let's see which case we're dealing with here. To determine this, I'm going to draw the angular sectors that I am breaking up my region into. And we can see that those angular sectors hit both curves, our inner curve being r equals 1/2, and our outer curve being r outer is equal to 2 sine squared theta. And so now using our formula, remember that our area of a polar curve, A in general for a single polar curve will be 1/2 r squared d theta. What we now will state is that our area is equal to 1/2 r outer squared, namely 2 sine squared theta squared, or 4 sine to the 4th theta, minus our inner squared, or 1/4 d theta. So now our one remaining task is to find our bounds of integration, and then we can go ahead and plug this into a calculator. The good news being that we can find our bounds of integration with a calculator as well. And so let's switch over to Desmos again. And so what I've done is we still have the graph of r of theta up. I've plotted r equals 1/2, and it seems at first glance, we should be able to find the point of intersection. But unfortunately, Desmos does not have that functionality. We can go ahead and quickly check, is this resolved if we write r of theta equals 1/2? And unfortunately, it is not resolved. So how do we deal with finding our points of intersection? So to find the points of intersection, instead I'm going to plot everything as a function of x. So we're going to indicate 2 sine squared x, and I'm going to indicate y equals 1 over 2, and then find our points of intersection that way. And so we can see that our first point of intersection is at pi over 6. With a second point of intersection at 5 pi over 6. And so these seem to be our points of intersection. However, let's take a moment to double check this. And how do we double check this? We'll jump right into our graph here and plot pi over 6 to 5 pi over 6 and just confirm that this traces out the correct segment. And here we'll go as well from pi over 6 to 5 pi over 6. And indeed, this is tracing out the correct region. Now let's go ahead and compute this integral. So I'm going to do the integral pi over 6, 5 pi over 6, 4. And be careful, Desmos sometimes has difficulty with higher exponents. So instead of writing sine to the 4th theta, I'm doing sine theta to the 4th minus 1 over 4 d theta. And there we have it. We're straightforwardly given an answer, 4.13. And so in terms of showing our work, extremely important. You've done your work in the calculator, but show your setup. So add your bounds of integration here, pi over 6 to 5 pi over 6, and state your final answer, which we found to be 4.13. Moving on to part C, we're told it can be shown that dx by d theta is equal to 4 sine theta cosine squared theta minus 2 sine cubed theta. And we're asked to find on the interval between 0 and pi over 2 to find the value of theta that corresponds to the point on curve C that is farthest from the y-axis. And we're asked to justify our answer. Now, before we dive into computing this, let's just very quickly look at the graph so that we understand what it is we're looking for. And so looking at our graph, which I've now graphed specifically on the interval 0 to pi, we're looking essentially for a point right around here, which is the farthest from the y-axis. This is a problem that becomes easy to overcomplicate. Notice that this is a maximization problem, farthest from the y-axis, but it's actually a simple one. The point which is farthest from the y-axis has max x value, which means if I want to know the maximum of x, I'm looking specifically the maximum of x as a function of theta because x is plotted as a function of theta. I want the critical points. In other words, I want to know when dx by d theta is 0 or undefined. And so effectively, we're simply looking for when 4 sine theta cos squared theta minus 2 sine cubed theta is equal to 0. Specifically, we're looking for solutions in the first quadrant. And so this is a computation problem. So let's jump right back to Desmos. And so we're looking for when our derivative is 0. In other words, we're looking for when 4 sine of x times cosine of x squared. Let's make sure to throw some extra parentheses in there just to be uber safe. You don't want to overthink your parentheses on an exam. We want to know when that is equal to 2 sine of x cubed. And so let's find our first solution, or specifically our first solution in quadrant 1. And we can see that this occurs at x equals 0.95. So let's quickly note that down and double check our work on our original graph. So we've proposed that theta is equal to 0.95 is the relevant solution. I'm going to get rid of these graphs and bring back our original graphs. And let's plot theta equals 0.95 So we go ahead and try putting that in, but we'll see that Desmos actually has trouble plotting that. So if you recall, the way to plot this would be to say that y is equal to tan of 0.95 x. And indeed, that seems to work well. And we can see that it does seem to line up with the point which is farthest from the x-axis, or sorry, the y-axis, at least visually. Now, it's quite easy to just wrap things up here and state that theta is equal to 0.95. But note that we were asked to justify our answer, and that specifically we are looking to find the max value on a bounded interval. And so make sure that you also address the endpoints, namely address that f of 0 will in fact be 0 if we simply go back to our function, our sine squared function. And if f of 0 is 0, then therefore that gives us r equals 0, which gives us x equals 0. And if we look at f equals pi over 2, our other endpoint, in that case, our radius is 1. However, x, which is 1 cosine pi over 2, is still 0. And so we can see that indeed we have found the global maximum on our interval. I will leave it to you to actually write this up in a paragraph response. Last part D. So we're told that a particle travels along the curve C such that d theta by dt equals 15. Already, that alone is making me think this is probably going to be a related rates problem. Find the rate at which the particle's distance from the origin changes with respect to time. So we're being asked to find dr by dt, evaluated when theta equals 1.3. And we're asked to show the setup for your calculation. So indeed, this is a very classic related rates problem. We're given a rate, namely 15. We're asked to find another rate, dr by dt. And can we relate the variables r and theta? Yes, we can. We've been given r of theta is equal to 2 sine squared theta. So let's go ahead and implicitly differentiate it. On the right-hand side, we have dr by dt. On the left-hand side, dr by dt. On the right-hand side, 4 sine theta cos theta d theta by dt. And make sure to review implicit differentiation and related rates if this doesn't make sense. All right, we've been given d theta by dt is 15, so 4 times 15, we'll have 60 sine theta cos theta is equal to dr by dt. And in fact, we don't even need to use Desmos for this. We can simply state that dr by dt is equal to 60 sine 1.3 cosine 1.3. And there we have it.